Section 9.7, we're going to work on complex numbers. The overall goal of this section will be to multiply, add, subtract, and divide complex numbers. We'll also look at powers of something called I. Now, I'm going to start kind of a little bit unconventionally. I want to start with some fun stuff. This is called the chaos game. So what happens is that you pick a point, plot that point, and then you roll the die and you move halfway from whatever your point is to the next point. Now, I'm not going to do this by hand, so let's do it with the computer. Let's add 10 dots and see what we get. Well, doesn't look all that exciting, so let's add a few more dots. And more. And the pattern looks like it's slow to emerge, so let's speed this up. Let's add maybe 100 dots. Vaguely looks like there's a pattern now. Let's bump it up some more. Add 500 dots. Does it look like there's a pattern emerging here? Yeah, triangles and triangles. Now, this is really all happening at random, yet there's some order to it. Now, eventually what you're going to get is something that looks like this. It's called the Sierpinski's triangle. And the Sierpinski's triangle is an example of something called a fractal. And fractals are really, really cool. They have all kinds of amazing shapes. And the thing that I want you to get here is that what defines a fractal is it has a self-similar shape. That is, if you take a magnifying glass and zoom in on any little piece of it, any little piece of that is going to look like the entire image. So it's kind of a self-repeating pattern. And that's kind of cool. And let's apply that to something a little bit more intricate. This is one of the first and most studied fractals that there are. It's called the Mandelbrot Set. And the reason I'm showing this to you now is because the Mandelbrot Set is built up out of complex numbers, the kind of things we're going to study. So let's watch as we zoom in on the Mandelbrot Set. Now keep in mind the original shape here, that original kind of three-lobed body with the antenna there. And watch what happens as we zoom in. Oops. And there you see that shape again repeating itself. And let's keep on zooming in. Now you're going to start out with a view of kind of like a soccer field and zoom in to something less than the size of an atom. You're going to zoom in tremendously. And yet you're going to see that same pattern and repeating again and again and again. You see it in a couple places off in the antennas. But it's just amazing. If you wanted to look up this online, Mandelbrot. He was a Polish mathematician who worked on this stuff for quite a long time. This is actually relatively recent mathematics. This stuff came around in the late 20th century. So in studying this, you're kind of catching up to the forefront of math, which is cool because math's been around for a few thousand years. And generally speaking, you don't get to see much stuff that's really that recent in the math class. So keep on zooming in. And it's just amazing. It'd be nice to know how far we're zoomed in at this point. Tough to tell. But just look at how complex these shapes are. And yet, as you keep on zooming in and in and in and in, at the end of this, you're still seeing stuff that's similar to what we started out with. Kind of getting anxious for the happy ending. Alright, so yeah, we're going to fast forward a little bit. Keep on fast forwarding, and there you go. Zooming in millions and billions of times, you see the same shape that we saw originally, and that's Benoit Mandelbrot. So kind of cool stuff. And like I said, if you look up fractal of the day, you'll see all kinds of cool images. Let's just do a quick search for fractals. And then click images. And you'll see all kinds of really wild and bizarre shapes. Now these shapes are brought about and rendered through complex numbers. So let's study complex numbers and understand what they are. So let me switch back over to here. We're going to look at a couple different equations to start with. X squared equals 25 and x squared equals negative 25. Now this is really in anticipation of stuff that we're going to do in section 10.1, so it's not that bad to kind of fast forward things. If you were given an equation like this, probably the easiest thing to do to solve it would be to do what? Square root on both sides. Good. Except unfortunately that only gives you one solution. In a quadratic equation, there's two solutions. So our workaround is to remember that we need to take the plus or minus square root on the right hand side, and then we get x equals plus or minus 5. Okay. So that works great. Mathematicians were really happy with that for centuries. But what about over here? There's a problem here, right? Problem is, up till now, we've affectionately called this NARN. Not a real number. Now that's not saying that there's nothing there, that we can't do something. We're just saying it's not a real number. And that's where we're going to launch ourselves into complex numbers. We're going to make ourselves a little definition. The square root of negative 1 is going to be called I. Now, I presumably is short for imaginary. Because when mathematicians like Girolamo Cardano in the 14th and 15th century started working with this, people didn't like it. They just thought, oh, it's ridiculous, it's imaginary. They didn't like it, and they rebelled against it. It took them, a century or two before they accepted this. But, the name stuck, imaginary numbers. So let me peel off the square root of negative 1 here. Let's write that as a square root of 25 times the square root of negative 1. And now I can simplify both of these. That's plus or minus 5 times I. And that's your solution. Wow, cool. But does it work? Well, probably the most important fact to go along with this, that the square root of negative 1 equals I, is this. What do you get when you square both sides of this? And when you square a square root, those operations are inverses of each other. They undo each other. This is an idea that we're going to see later on at the end of section 10.7 maybe? Somewhere around there. But anyways, when you square a square root, you just get what's underneath that root, radicand. So I squared is negative 1. And these two things you can star in your notes. Those are the two most important things that drive our work in this section. So with this, let me check that our answer actually works. So let's take 5i and square it and see if we get negative 25. Well, it's going to be 5 squared, I squared. 5 squared is 25, but what's I squared equal to? Negative 1. So it works. Hey, 5i is something that you could square to get negative 25. And it wouldn't matter if I squared negative 5i because that negative would cancel itself out over here. So both of those answers work. Yay. So let's play around with this a little bit more. Try and get comfortable with this idea of I. Whenever you're working with a negative underneath the square root, split off that negative right away. Do not do anything else first. Do not pass go. Do not collect $200. Split off the square root of -1. So I'll write that as the square root of 4 times the square root of -1. Haley? Oh, I thought you gave the answer. Somebody get. Yeah. 2i. Cool. No, you don't need the plus or minus. Thank you. Let's try a similar one. Problem number 20. Square root of -11. Well, kind of like the last one, we'll split off negative. But unlike the last one, that first part doesn't simplify. Square root of 11 is just square root of 11. So that's okay. But I still get some simplification, right? Where's the simplification? I. Now, generally speaking, you write the numbers, then I. With square roots, I kind of make an exception. And I'm not the only one that would do this. Sometimes I'll write I times the square root of 11. The reason for that is because it's very easy to get a little sloppy and extend that square root over the I. And that's wrong. In this class, we will not take the square root of the square root of -1. You're not going to have I underneath a radical. So I sometimes tend to like to write the I out front, even though, technically speaking, a lot of mathematicians might not like it. That's okay. How are we doing so far? Good. All right. Let's take a look at problem number 22. Square root of -28. We're going to break this up into 3 radicals. Can you tell me what we're going to put in any of these? All right. So let's see. Let's put the -1 here. So that's the I that you're talking about. And then a 4 and a 7. I put the 7 last just because that's not going to simplify. The -1 you could put in a couple places, but I like it out front for reasons that I just mentioned here with problem number 20. How does that simplify? Yeah, 2i times the square root of 7. Yay. And that's it. Okay. Let's try one last one. Problem number 28. Negative the square root of -121 over 144. This is a good one. One thing that's a little tempting is to think that these negatives cancel each other out. They don't. They can't. You can't cancel the negatives because one's inside, one's outside. So instead, we'll leave that alone. I'll split up the numerator and denominator. See if you can't race me to the answer. I assume it was for me. Okay. Okay, so the negative stays out in front. That's 11i in the numerator over 12 in the denominator. So spot on, Melody. Thank you. Nice. So this is a little introduction to I. Where it becomes a little bit more useful is when we generalize it into something called complex numbers. But are you okay with I? Liking I so far? Okay. All right. Remember in graduate school one time, walking through the staff lounge, and I grabbed a cookie. And the department chairman was right there. He goes, "Oh, hey, Jeff, going to the seminar? Because if you take the cookies, you got to go to the seminar." And the seminar discussed something which sounds stupefyingly boring. Fluid flow past a blunt object. But, I had to go. And actually what was kind of cool was they talked about why people put dimples on a golf ball. Now, a lot of people would probably say, oh, to make it go farther. The explanation was actually pretty cool, and it involved complex numbers. It showed really detailed information as to why you put them there, and even went so far as to discuss things like the big giant red spot on the planet Jupiter. So it's pretty cool. And all that analysis relied on complex numbers. So lots of cool stuff. But complex numbers look like this. They're going to be a plus b times I. Oh, thank you. Thank you. So a plus b times I, where a and b are the real numbers, things that you're familiar with. And I equals the square root of -1, of course. So let me give you a few examples. So 3 plus 7 times I. 4 minus 5i. 8 plus 0 times I. Of course, 8 plus 0 times I you could just write as 8. And what this is showing you here is that the real numbers that you're familiar with can really be thought of as a special case of complex numbers. You could have 0 minus 6i, or just minus 6i. So this is considered a purely imaginary number because the real part is 0. And I should mention a little bit more about the anatomy of these complex numbers. This is what's called the real part, and this is the imaginary part. So you get a real part and imaginary part. And together, those two numbers make one complex number. So as I said at the beginning of this, our goal is to add, subtract, multiply, and divide complex numbers. Let's start with problem number 38. Eight plus 3i plus -7 minus 2i. This is not much more than, adding like terms like you did with polynomials in Math 1100. So let's look at the like terms. The like terms are the real parts. So the 8 plus -7. What's 8 plus -7? 1. And then likewise, the complex parts. 3 plus -2 is, 1. So 1i, and if you just wanted to write plus I, That's the way I'd write it. If you want to write the 1 there, that's fine too. So 1 plus 1I. And I'm afraid that's it. We're done with that one. Cool. That's all there is. We can't do anything else because these aren't like terms. In order to add these, I'd have to have like 3I plus 1I or 3 plus 1. But I can't add 1 plus I. They're just not like terms, so we're going to leave it like that. Dead throw? Question? Okay. So let's try another one. Problem number 40. 5 plus 3I minus 6 minus 9I. So we added complex numbers. Now we're subtracting complex numbers. I guess what I would suggest is this, that you distribute that negative. Minus 6 plus 9I. So Logan, what do we get when we combine the like terms here, please? Good? Good. So, thank you. Negative 1 plus 12I. Nice. Want one more adding and subtracting complex numbers? Let's take a look at problem number 44. Negative 7. All right. Is it negative 7? Yeah, negative 7 plus the square root of negative 81 plus negative 2 minus the square root of negative 64. What do you think we have to do first? Yeah, we need to get rid of the negatives underneath the square roots. Rewrite them using imaginary numbers. So, negative 7, square root of 81, square root of negative 1. It's going to be negative 7 plus what? 9I. Thank you. Now, maybe you're good enough to kind of jump down to here. Negative 2 minus what? What's the square root of negative 64 going to simplify down to? 8I. I don't need to see that step. If you want to rewrite it as the square root of 64 times the square root of negative 1 and then simplify it, that's fine. Alexis, what do I get when I simplify this? Good, negative 9 plus I. If you want to write negative 9 plus 1I, that's fine too. Okay. Let's step it up a little bit. Actually, you know what? I'm going to do one follow-up problem. Problem number 46. Square root of negative 9 times the square root of negative 100. Now, let me show you how not to do it first. You don't have to copy this. You could say, oh, well, that's negative 9 times negative 100, which is the square root of 900, which is 30. That's wrong. If you think back to when we first started working with these things, what did I say to do when you had a negative underneath the square root? Yeah, break off that I term. So this is square root of 9 times square root of negative 1, square root of 100 times square root of negative 1. Okay. Now each of those terms simplifies. Nikki, How do these simplify? Not 9. 3i. Good. Times 10i. So 3i times 10i would be 30i squared. Does anyone remember what I squared is? Negative 1. So the correct answer here should be negative 30. Like I said, when you're dealing with these negatives underneath the square root, split them off right away. Otherwise, there's going to be problems. It's 30 times the negative 1. Because I brought these together. I times I was the I squared, and then 3 times 10 was the 30. I squared gets replaced by negative 1, because those two are equivalent. So then 30 times negative 1 is where you got the negative 30. All right. Let's finally do some multiplication. Problem 56. And this is actually a good reminder right here. I squared is negative 1. Let's keep that in mind as we do 56. Two I times 7 plus 2i. Now it asks us to do the multiplication and simplification here. What multiplication is there? Yeah, thank you. Distribute. So that term out front has to multiply both of these terms in behind. So, okay, cool. What do I get when I distribute that? 14i plus 4i squared. I like that you gave me the 4i squared, because you get the I times the I is I squared. But we shouldn't leave it just like this. There's a little bit more work that I would expect. So what else should I do? All right, 14i, and somebody's really good at this already. That's really 4 times negative 1, or better yet, just negative 4. There's one last thing that I'll ask you. I wouldn't mark this wrong, but it's always nice to keep your instructor happy. Complex numbers are written in the form of a plus bi. That is, you're going to write the real part first and the complex part second. So negative 4 plus 14i. And the reason to try and keep this straight goes to physics. There's a lot of applications for complex numbers in physics, and the real part and the imaginary part have much different meanings, so you want to keep those things separate. By the way, remind me later in this course to point out the use of I in an episode of The Simpsons. So I actually makes a cameo in The Simpsons, which is just amazing because it's a rather lofty math notion to be in an episode of The Simpsons. Let's try problem number 60. Three minus I times 2 plus 3i. Okay. Well, what am I going to do here in terms of multiplication? Well, yeah. Distribute. Or what's the word that we use when we multiply binomials together? FOIL. All right, so first terms give me a 6. How about the outside terms? Thank you. Is that sincere? Thank you. 9i. Middle terms? Minus 2i. Excellent. One of the biggest mistakes I see in these problems is that people forget that there's an I squared there at that last bit. Now there's a couple things that we should do as we work through this to simplify it. Does anyone see one of them? All right, there's an I squared. There's something else too that we can take care of. Perfect. Combine the like terms. Now, it's up to you. Maybe you'll get good at this. Maybe you're more comfortable taking your time. But just like this one, I squared is negative 1. Negative 1 times negative 3 gives me positive 3. And here's a 7i. So I'm almost done. There's one last thing that I would ask that you do. Yeah, combine like terms again. 9 and 3 gives you, or 6 and 3 gives you 9. Nice. That's what I'm looking for. 9 plus 7i. How are we on that one? Pretty good? Yes. All right. Let me test you. Let's take a look at problem number 64. Three minus 2i squared. Now, one thing that it is not is 9 plus 4i squared. You can't take that shortcut. Sorry, doesn't work. Yes, that's exactly what you have to do. You have to FOIL it. So you're going to rewrite it as 3 minus 2i times 3 minus 2i. Does everyone have a calculator today that needs one? This is my low-tech solution to the fact that my software doesn't have a pause button. So when you're watching the videos and you see this message says pause, just lay on the fast forward button until the pause disappears. So good. Good. All right. Looking good. Okay, so let's see what this works out to be. 3 times 3 is 9. Outside gives you minus 6i. Inside gives you minus 6i again. Minus times a minus is a plus 4i squared. Now, like a lot of these, you're going to get some simplification because of the like terms. And you're going to get some more simplification because of the I squared. So 9 minus 12i minus 4 gives you a total of 5 minus 12i. How many people got that one? All right, cool. Now I'm going to make a little deal with you. Here's the deal. I will show you how to check this on your calculator. You just make sure that you show me the work on the exam. Fair enough? All right, cool. So type in a left parenthesis, 3 minus 2, and we need to figure out where I is. I is right above the decimal point. How do I get to I if it's above the decimal point like this? Second. Notice that it's actually color coordinated. This is in blue, so to access it, you hit the blue button. Second I, parenthesis, and then hit the square key, fifth button down on the left. Press enter. Okay. Ready? Go. Go. Yeah, all right. Well done. Well done. Thank you. All right, so a nice, neat trick. You can check your answers here. You can multiply complex numbers together, too. So it's a nice little trick. I still want you to know how to work with them, though. So make sure you practice it a little bit. Let's do this. Let me introduce something called conjugates. So if I have a number a plus b times I, its conjugate is going to be a minus b times I. Let's FOIL those things out together, because something special is going to happen here. A times a is going to be a squared. How about the outside terms? What will I get there? Minus abi, good. Plus abi, good. And someone else for the last term. Minus b squared I squared. Excellent. You have to be careful with that last one. It's minus b squared I squared. Now something special is going to happen here in terms of simplification. What's the first thing that you see? Yeah. Hasta la vista, baby. Those are gone. Those cancel out. That's cool. What happens to minus b squared I squared? This would be minus b squared times negative 1. And then a little bit more. A squared plus b squared. Wow. So a long time ago, when we were factoring things, I said that this was prime. But if you were really close to me and heard me, I whispered over the field of real numbers. Which was kind of my out saying, well, you can factor it if you allow for complex numbers. This is the sum of squares. Up until now, I've said, gee, this is prime. Now we won't use this to factor complex numbers and polynomial expressions, but you could. The importance here, though, is this. When you multiply a number by its conjugate, check out what happens. There's no more complex part to this, right? The I is gone. It's just a real number. And that's actually kind of cool. So let's try that with a quick example. Let's try 4 minus 5i. What would be the conjugate of 4 minus 5i? 4 plus 5i. Multiply those together. See what you get. you should have something that looks like this. 16 plus 20i minus 20i minus 25i squared. It's important to get that I squared. Now, as with our previous example, these two things cancel each other out. Minus 25i squared, what happens to that? Becomes plus 25, which gives you 41. So that's cool. You started out with two complex numbers, but you end up with a nice simple real number. And that's a useful result. And we're going to use that for the second to last topic in this section, which would be division of Rash or of complex numbers. So let's try problem number 70. Oops, not 2, it's a 4. All right. 4 divided by 2 minus I. Yeah. Well, technically speaking, this is the square root of negative 1 in the denominator. Not that you should ever revert back to writing as the square root of negative 1. Just leave it as I. But that is a square root in the negative in the denominator. We don't like square roots in the denominators. So I need to get rid of that. And my trick will be to multiply by 1 in the form of something over itself. Because multiplying by 1 doesn't change the value of anything. If your boss multiplied your check by 1, you wouldn't suddenly put them on your Christmas card list. All right? It hasn't changed anything. So what form of the number 1 should I choose to multiply by here? Thank you, ladies. 2 plus I over 2 plus I. Basically, it's the conjugate of this term here in the denominator. Now, in the numerator, I'll distribute that 4, 8, 8 plus 4i. In the denominator, I get to do a little fussing around. It's going to be 4 plus 2i minus 2i, and then what? Thank you. Minus I squared. Now the nice thing, and of course it's predictable, is that these two terms here in the middle cancel each other out. That's what's really cool about multiplying by the conjugate. That leaves me with 8 plus 4i over 4. All right, now I've got a couple ladies up front that have been helping me out a lot. How about somebody else? What's left in the denominator? All right, so 4 plus 1. Thank you, ladies. So 8 plus 4i over 5. Now, I'm fine with it like this. But as I mentioned earlier, a lot of times there's applications in physics for these things, and they really like it broken up into a real part and an imaginary part. So they'll do it like this. 8/5 plus 4/5 times I. It's not something that I'm worrying about because our applications are math, not physics. But either one of these is fine. Just be aware of that if you check yourself someplace that you might get something like this as opposed to like this. I think that'll even work on your graphing calculator. Let's just try it out. 4 divided by parentheses 2 minus I. And you get something that looks like this. If that's not too recognizable for you, hit the math key right here. Then you get a window like this. Press enter twice, and oh, that looks a little bit more recognizable. Pretty cool. Again, let me emphasize, on the test, I still want to see your work. But but I have no problem with you checking your answers. Make sure you get them right before you hand it in. That'll make two of us happy. Okay, let's try another one or two like that. Let's try number 72. Two I divided by 3 plus 8I. This one's going to have a little, let's see, it's going to have a little, let's see, 964, nah, we'll be okay. Why don't you work on this one? Mimi and I will walk around and try and help out. Start out by multiplying by the correct term. All right, looking good on this one. So the conjugate here is 3 minus 8i over 3 minus 8i. let's distribute the numerator. I'll get 6i minus 16i squared. In the denominator, it's going to be 9 minus 24i plus 24i minus 64i squared. So lots of simplification here. In the numerator, what happens to the minus 16i squared term? Yeah, it just becomes plus 16. So it's negative 1 times this, which is going to be plus 16. Also in the denominator, we get some cancellation that we're used to. And then we have 9 plus 64 is 73. I'll reorder these to put them in the form of the real part first, the complex part second. Some of you went so far as to rewrite it like this, and that's fine. It's awesome. Either one of these would be fine for an answer. I'm very happy with that. I even saw a couple of you checking them on your calculator, and that's great. So if you were to do that, it looked like this, at least initially. And that looks pretty ugly. You're like, oh my God. But then you hit the math key, press enter twice, and you get something that looks a little bit more reassuring. So nothing wrong with you checking your answers, just as long as you show your work. There's one last little thing to cover here. I think I should probably do one last division problem. So let's do one last division problem, then we'll do powers of I, and we'll finally be done with this section. So that last division problem is problem number 76. 2 plus 3i over 2 minus 3i. What am I going to multiply by on this one? Alice? What would be the conjugate? Actually, you're just going to base it off of what's in the denominator. So what's the conjugate of the denominator? 2 plus 3i. 2 plus 3i. Now, it's an interesting twist or coincidence that the numerator is the same thing as what we're multiplying by here. That's okay. So in both the numerator and denominator, we're going to have to FOIL this thing out. Okay. Let's do this together. Let's start in the denominator. 4 for the first terms. What's the outside term? All right, you guys seem determined to work on it yourself. Don't let me stop you. All right. All yours. Okay, so the terms that you get in both the numerator and denominator are actually going to be pretty much the same. The only difference is in the numerator, all the signs are positive. In the denominator, a couple are negative, a couple are positive. So, oh well. Now in the denominator, we're going to get a lot of simplification, and we will in the numerator as well. It's just going to look a little bit different. In the numerator, I can add up the like terms. I get 4 plus 12i minus 9 over 4 plus 9. So overall in the denominator I get 13. In the numerator I get negative 5 plus 12i, or negative 5 over 13 plus 12 over 13 times I. Okay. Again, this is something you can check on your calculator. That's kind of cool. It's nice to know that you got these problems right before you hand them in. How are you doing on the division of complex numbers? Okay? All right. There's one last thing we're going to cover here. I know that you're probably getting kind of anxious, so let me just divert for a second. I talked about fractals having lots of uses. Let me see if I can't find my little thing on fractals here real quick. Fractals. Julie Set means. No, this isn't the one I wanted. Fractals. No. Rats. I'll have to look for it in a little bit. I know that there's a lot of fractals actually in nature. I don't know what fractal tree. That's kind of cool. There's actually research into using fractals, which really are generated by equations, to represent pictures. So if you could send across the internet, instead of a large picture file, if you could send across a few equations to generate something, it could save a lot of space. So desktop, let's see. Yeah, I'm not seeing where it is right now. So, okay, one last, excuse me, one last little topic here, and that is powers of I. Now, really, the only power of I other than I itself that you need to know is I squared. We've practiced with this enough that I'm not going to bug you for it. I squared is negative 1. And our goal is to use that to simplify other things. To simplify, for instance, in problem number 96, I to the 200th power. Wow. That looks like a pain. But here's the trick. We know what I squared is. So I'll write this as I squared. To what power would I have to write that? To the 100th power. Why does that work? What happens when I remove the parentheses? What do these exponents do? They multiply each other, right? So that's 100 times 2 is 200. So these things are equivalent. But here's the genius of this. We know what I squared is, right? I squared is negative 1. Without your calculator, what's negative 1 to the 100th power? It's just 1, right? Cool. Wow. Done. All right. It's a little slow. All right, I understand. Let's try another one similar to that one. I'll let you try it. Problem number 92. I to the 22nd power. Do exactly the same thing. Start out by breaking it up with an I squared. And then simplify it. And then simplify it again. Joe, what power should I put on the outside? And what's negative 1 to the 11th power? Perfect. So if it's an even number here, you get a positive 1. If it's an odd number here, you get a negative 1. Thanks, Joe. Okay. 2 more. Problem number 94. I to the 97th power. Uh-oh. There's a problem here. 97 isn't a nice even number, is it? How annoying. How rude. So here's the trick. Almost kind of feels like a teenager's way of getting around something that the parents told them to do. Like, okay, fine. I'll just write that as 97 is 96 plus 1, right? So when I multiply things at the same base, I add their exponents. But in writing it like this, now I can concentrate my effort on this part. The I to the 96th power. That we can deal with. The I to the first power, we're just going to leave by itself. I to the 96, let's rewrite that. What should I put here? I'll rewrite that as I squared to the 48th, which is negative 1 to the 48th. Now this I is still coming along for the ride. That's okay. Still there, that's fine. What's the final answer here? Just I. Excellent. What's that? There's another way to do these. It requires memorization and division and remainders. Okay. All right. But notice what we're doing. It's the same thing all along. You just got to get an I squared term, and then you simplify the I squared. I squared is negative 1 to some power. We're done. So, all right. So last one then would be problem number 90. I to the 19th. How should we start this one out? 19 is not a nice even number like the first two. Thank you, Deja. I to the 18th times I. Nice. Now that I is just going to kind of come along for the ride the rest of the way. This is an I squared. So how does this one finish up? I squared to what power? 9th power, which is negative 1 to the 9th power. What's negative 1 to the 9th power? Negative 1 times I, which is negative I. If you look at all our results together, there's 4 different possibilities when you do these types of problems. 4 different possible answers. You could get 1. You could get negative 1. You could get I. Or you could get negative I. So one of those 4 possible answers are what you're going to get when you do a power of I. Just a power of I. Maria was asking earlier about this. It's like, oh, I don't like these. I understand. There's other ways to do it because there's a pattern here. I squared, of course, is negative 1. I cubed would be negative I. I to the 4th power is 1. And then it starts all over again. I, negative 1, negative I, and 1. I to the 9th, I to the 10th, etc. Doing it this way would involve memorizing these first few terms and also dividing by 4 and figuring out where you are in the sequence. You can do that. People do that. There's nothing wrong with it. I used to teach it that way, but I guess I like this because you only have to remember one thing. I squared. I squared is negative 1. And that's it. Once you have your I squared term split off, it's just negative 1 to some power, which you can simplify. All right, for homework. Try 15 through 29, 39 through 45, 71, 77, 83, 89, and 95. Let's just make that the odds, okay?